Hello again. This is going to be our session regarding to chapter 4. And remember, we have studied the random variables, starting with the discrete random variables, then with the continuous random variables. And if you remember, many probability calculations related to continuous random variables are involving with an integral calculation. And sometimes it may not be very easy to calculate the integrals of some probability density functions. Therefore, calculation of probabilities regarding to some types of continuous random variables, they require a computational software such as R. And here we are going to practice a few probability solution example and also calculation of expectation and variance regarding to a complex non-differentiable probability density function. Now, please check this example. Let's just say we have a continuous random variable x, and its probability density function is defined within the interval of 0 and 4 as 8 minus 3 in square root 2 times the absolute value of x minus 2 over 16. Now you see, we have such a complicated probability density function. It has square roots, it has absolute value inside it, and therefore integrating such a function can be a little troublesome. Therefore, if we are supposed to answer a question, a probability question related to this probability density function, then it may be a good idea to practice the solution using a programming language such as R. Now, what we know about this probability density function or this random variable, this random variable can only take real values within the 0 and 4 interval. It cannot take any other possible value. Therefore, the probability density function is equal to 0 elsewhere. Now, the question asks us to write down an R function. And we are going to name this function as f, just like it is here. And this f function will be exactly computing this probability density function for any real value. So if the input is between 0 and 4, then it is going to calculate the PDF using the above function. If it is something else outside this interval, then it is going to return us as 0. Now, it is very important at this point to not use an if and else statement in such a function. Now you see, maybe you can think about writing a function with an if else statement such that it calculates this function if the values are between 0 and 4, else it returns a 0. But we are not going to do this. Rather, we will use logical expressions. Okay. Now, I think we are ready to practice this. Now I'm just going to use for our session, our environment, and I'm just going to open a new script. And in this new script, I am going to write down my function. So I will say that my probability density function f is going to be a function with input x. And depending on the fact that x is between 0 4 interval, within the 0.04 interval or not, it will return the function itself or it will return 0. So let's just write the function itself. It was equal to 8 minus 3 times square root of 2 times the absolute value of x minus 2, and this was just divided by 16. Okay, so you see we have this value. How many parentheses we have written here? Yes, and I guess it will just work without this parentheses. Yes, there are 3 parentheses closed, and okay, yes, I need to eliminate this one as well. So 1, 2, 3, and yes. So this is just going to be the function that will be returned if the input x is between 0 and 4. However, otherwise, it's just going to return a 0 value. So we will write something else here. We will write additional components, and we are going to multiply this value with a logical expression of x being greater than or equal to 0. In this case, if you do it like that, if x is less than 0, the logical expression here will return a false. Therefore, all calculation here will be multiplied with 0. So false means 0. So whatever this value is for a negative value, it does not matter. Since we are multiplying this function with this logical expression, whenever the input value is less than 0, we are going to get a 0. However, if it is greater than or equal to 0, we are going to get this function, because when x is greater than or equal to 0, this logical expression will return a 1, okay, which is an ineffective component in a multiplication operation. Now, this is not enough, of course. We also need to write x being less than or equal to 4 as well. Now, according to these two logical expressions, if and only if these two logical expressions both are equal to 1, then we are going to get the result coming from that function. So you see, if x is within the 0-4 interval, then we are going to get this function. However, if x is less than 0, or if x is greater than 4, one of these two components is going to return us a false, therefore 0, and the result is just going to be 0. So this is how we can express the probability density function. Now let me show that to you here. The probability density function here is exactly written as a function here. Now we have our probability density function. In fact, we can use it to compute the probability density value for several values. For example, for a negative value, such as -2, which is just going to 0. If we are interested in the probability density function at 1, we are going to get the exact return value by the function. At 3.5, we can get a value, or at 4, in fact, we can get a value. However, for a value that is greater than 4, such as 4.75 or even greater, we are going to get a 0. So the function is perfectly working. So the next thing that is required by this exercise is to draw the probability density function. Now, our objective here to have an idea about the structure of this PDF. Now, you see, we know that this random variable is taking real values between 0 and 4 according to this PDF. But if we do not draw the PDF, we do not understand from which region we are likely to get more values in the realization of this random variable. Is it more probable to get values closer to 0 or 4, or is it more probable to get values in the middle? We need to understand it, and we can only understand it by drawing the PDF. Now, how are we going to do this? So the idea is explained here. First of all, this function is defined within the 0-4 interval, so there is no necessity to draw the function in the outer regions. However, just to see that in the outer regions we are getting a 0 value, we are going to draw this function between -1 and 5 values. Therefore, what we are going to do is this. We are going to create a xvec vector, a vector named as xvec. It doesn't matter what you name it. So this xvec vector is just going to create 10,000 equidistant points between -1 and f. So starting from -1 until 5, this vector will contain an ordered sequence of real numbers, but 10,000 of them. So the distance between each consecutive number is going to be determined by dividing 6 to 10,000. Okay. And we are going to evaluate the probability density function for all these values between -1 and 5 using xvec, and we are going to store the response at yvec. Then we are going to use the plot function in R to plot the x vector versus y vector on a two-dimensional domain. Okay. However, we need to know how to use the plot function. Therefore, first first, what we are going to do is we are going to write a question mark plot on the R console, so it will direct us to a browser. It will direct to a web page where we can learn about how to use plot function. All right, let's practice this. So what we need to do is to draw this function. First, we need to create an X vector that consists of 10,000 points between -1 and 5, and we can do this by the sequence command. So between -1 and 5, the length out of this vector will be 10,000. So we have 10,000 equidistant points in this X vector. In fact, let's just see the first 5 elements of this vector. As you can see, it starts from -1 and it increases by 6 over 10,000 at each step. Actually, not exactly 6 over 10,000, but maybe a little less than that. All right, so this is our X vector. And the Y vector, the response will be calculated as the f of X vector. So these are just going to be the responses. So we calculate that. In fact, we can see the first 5 elements of this vector. Of course, they are all going to be 0 because at these 5 points, the probability density function must return a 0 value. Okay. Okay, so we have seen that. Now we need to use the plot function, but in order to learn about it, we write question mark plot, and you see a web browser opens in our computer, and you see there are many. So let's, I'm sorry, not this one, but generic XY plotting here. There's another link here, which is the plot scheme in the graphics library, but we do not have that library. So we are just going to focus on the base library here. And in the generic XY plotting, we need to plot the first vector versus the second vector. So X and Y are respectively determining the coordinates in the horizontal axis, the vertical axis, and then we are going to use the other arguments. Okay, now let's start with the simple. Let's directly use the plot X versus Y. Now I'm very sorry about this, X vec versus Y vec. In fact, let me sorry, let me write it here, then I can work it out. Now, if you plot X vec versus Y vec, you will see that there will be 10,000 small points plotted. As you can see, these are points here. 10,000 small points starting from -1 until 5. And we have a quite nice plot diagram. And the shape of this probability density function looks like this. However, one more thing that you can do in this plot figure is you can use a type argument. And in the type argument, within the quotation, if you write L, then you are going to get a line plot, which means the points are just going to be connected with each other, and you will get a line type of function. Okay, so this is how our probability density function looks like. According to this probability density function, the probable values between 0 and 4 interval are more frequently around 2 because the maximum density is observed at 2. And of course, the density values at 0 and 4, they are not very small as well, but relative to 2, it is less likely to get values closer to 0 and 4. So mostly in the realization of this random variable, we are going to observe much more values around 2. Okay, so this is how we draw our probability density function. And in fact, one more argument I can teach you. If you do not like the width of the line, you can change the line width to 3 instead of 1 by default, and you are just going to get a thicker plot. Okay, thicker plot to exactly see the behavior of the function. All right. Now, The next question that is going to be asked is what? We are going to calculate a probability. Okay. For example, what is the probability of x being less than or equal to 3? We are going to calculate this probability. So how we are going to determine that? You see, we need to integrate this weird-shaped function between 0 and 3, right? If we are interested in the probability of x being less than or equal to 3, we will be interested in the total area on the left-hand side of 3 under this function. And this requires the integration of this function from 0 to 3. Okay? And of course, for this weird-shaped function, which is also non-differentiable at certain points, it is just going to be a little troublesome if you want to calculate it theoretically. Therefore, we are again going to use the programming language here to calculate that. But for that, we need to learn about the integrate function. Okay, so integrate function helps us to calculate the integrals related to functions. Okay. So when you write question mark and integrate, you are going to get a web browser again, opening explanation about the integrate function. The first argument that you need to write is the function itself, which is going to be our probability density function. Then we are going to write the lower bound and the upper bound of the integral, definite integral. Now, the rest of the integrate function is not important at this point. So we are just going to continue by integrating for function f. For function f was defined by ourselves here. F between 0 and 4. So what would you expect to get here? So we are basically calculating the total area under the PDF between 0 and 4. In the rest of the region, we do not have any area under it. The result must be equal to 1, right? The total area under the PDF is always equal to 1. This is the golden rule of probability density functions. And if we do that with a small absolute error, you get 1. Okay, so this is a numerical error that may happen for such a function. It is just okay. Now we understand that this is a probability density function. And if we are interested in the probability of our random variable to be less than or equal to 3, then the next thing that we are supposed to do is we need to integrate this function from 0 to 3. Okay? And if you do that, you would get 0.8233 approximately, or 32 approximately, which is the probability of our random variable to be less than or equal to 3. If somebody asks you what is the probability of our random variable to be between 1 and 3, then you are going to integrate this function between 1 and 3. Okay? In that case, you would get a probability of 0.6465. All right, so this is how we can calculate the probabilities for such weird probability density functions. However, an important thing that I need to say at this point, if you have defined this f function using an if and else statement instead of the logical expressions here, then the integrate function wouldn't work. Okay, wouldn't work because you see, if you write this function in this form, then if you just give this function or introduce this function a vector of inputs, then it is just going to calculate every value for a set of vectors. So if x is a vector, as you can see, what we have done here is exactly that. So we have provided a vector of values from -1 to 5, too many real values, 10,000 real values. And in this command line, the probability density function is calculating the response for all of them one by one. Okay, so this function works for an input of vectors. Therefore, the integrate function would also work for this function as well. Now, let's continue to our practice. We have calculated the probability of x being greater, less than, or equal to 3. Now, in the next part, it asks what is the probability of x being greater than 1.5 Now, you can easily calculate the probability of x being greater than 1.5 by integrating this function from 1.5 to 4, and that probability is 0.6875. And what is the probability of x being between 1 and 2.5? In that case, we are just going to integrate that function between 1 and 2.5. You can get the response for all of these values. Now, the next thing is to calculate the expected value. And you remember, for a continuous random variable, the expected value requires the integration of the variable x multiplied with the PDF and integrated out over the domain of our random variable. Okay. Therefore, what I'm going to do here is I'm just going to define expected value function, the integrand of the expected value as x, ex, and that is just going to be a function of x again, which is calculating x times the probability density function as we have defined above here. Okay. And then the expected value of x is just going to be the integration of ex function between 0 and 4. Okay. But you see, let me copy that function first, and let me copy here and first run the integration instead of storing it. So when you integrate this function between 0 and 4, you get a value of 2. And actually, because this probability function is symmetric around 2, we can easily say that the expectation should be equal to 2 because it is the weight center of this function over the horizontal axis. However, as a result of the integrate function, you do not exactly get a single value. Instead, you get an expression. So you get a long sentence here. Therefore, if you want to store your expected value, expect x, and when you write expect x, you're also going to get a sentence. And if you want to multiply expectation of x with, for example, 5, you wouldn't get a value of 10 because this is just a sentence. It is not the value. Therefore, instead, we need to write here $sign value. So expectation of x will be equal to the integration of the ex function above, and only the value, the output value, will be stored. In that case, expect x is just going to be a value of 2. Now, this is how we perform the expected value calculation. Now, how can we calculate variance? Now, we are just going to use the convenient formula of the variance, but for that, we also need to define expected value of x squared. And for that, remember, which function should we integrate? We need to integrate x squared times the probability density function as defined above. And just like the above calculation, we will expect x squared as the integration of the x2 function between 0 and 4. And the value will be stored here again. And finally, we will write the variance of x is equal to expected value of x squared minus square of the expectation, right? And the variance x will be taken as an output. So let me perform the rest of the operation. As you can see, the variance of the random variable defined here is equal to 0.9524. Okay. Now you see, we have learned how we can plot a probability density function, how we can integrate it between intervals to calculate the probability of interest, how we can calculate its expectation, and how we can calculate its variance. So we are just going to meet again in the next video.